So my name is Brandon Dail, and today I'm going to be talking about a language called ReasonML. And Reason is a functional language. It also supports imperative patterns, and it has a lot of great language level features that I think make building web applications easy, and in a lot of cases fun. And I'm a software engineer at Formidable, one of the sponsors. Just a little bit about what we do. We are a consultancy dealing mainly with universal or isomorphic JavaScript applications with React at scale. So if that sounds interesting, come talk to me about it. And before I talk about Reason as kind of like a solution, as an approach to building web applications, I kind of want to set the context around why am I even here? Like, how is this even an option? And I think, this is basically it, right? Pretty much everyone here is probably using some sort of compiler, right? Who uses Babel? Yeah, you're going to use Babel. You probably use JSX. You might even be using TypeScript or another compiled to JS language. And what that really means is that we've kind of accepted the fact that we need a better source language for our applications. The version of JavaScript that we have to actually send down to the client to support all the browsers that we want to support is sometimes difficult to scale with. So if you're using Babel to use a newer version or TypeScript to use something with types, you've probably felt that way. This is kind of the stack for the solution that I'm going to present here today. And Reason is actually only one small part of it. So the components that kind of build this stack are first the language OCaml, which is a language probably not a lot of us have used if you've been using web applications or building web applications for a long time. It has mainly been used in academic settings or in other sort of niche or smaller communities, and sometimes in like finance programs. And then there is Reason, which is the reason that we're all here. And I'm so sorry if there's puns. It's sometimes unavoidable. And Reason is sort of an interface to that language. So Reason itself isn't a new language. It just provides a better syntax for an existing language. And then finally, Reason is great, OCaml is great, but I don't know of any web browser that runs OCaml. If you do, please send it to me. So the last component here is BuckleScript, which is a compiler that takes OCaml, or Reason code, and compiles it to really clean, idiomatic JavaScript. And I know this stack sounds kind of complex, because these are three different technologies, and each of them in their own, in isolation, are complex. So what I want to do is I want to take a second to try to outline exactly how they work, and at a high level understand technically how they interact with each other and how this is even possible. And to do that, I have to talk about the OCaml compiler. Now, a lot of what I'm going to say is pretty hand-wavy and ignoring a lot of really great technical detail, but this is kind of the basic outline of how the OCaml compiler works. And let me step through it step by step. And so the first thing, of course, the compiler takes some OCaml code as input, right? Like any compiler does. And then what it will do is this fancy compiler stuff like parsing, lexing, pre-processing, and it's going to output what's called an AST. If you've used Babel, you're probably familiar with that term. And in this case, it's an untyped AST. So that means that, well, there might be information about the types in this AST. They don't really have any value yet, right? So after that, OCaml will go ahead and perform type inference. And that's one of the best things about the language is that it has a really strong inference system, which means you get strongly typed programs without having to explicitly type a lot of your code. It'll also validate any existing or explicitly defined types, and then it will produce a version of that AST that has that information, as long as you didn't screw up and all your types are good. And then because OCaml is a really highly optimized language with a very complex compiler, it goes to the step where it turns that typed AST into something that's called lambda. And this is an intermediate representation that basically represents the same program in a little bit of a different way. It uses S expressions. And if you're not sure what those are, if you've ever used something like Clojure, where you have like parens that never end, that's basically S expressions. And then depending on your compiler, you can either go to native code or bytecode. And that's basically how OCaml works. So how exactly does Reason fit in there? Reason comes in at this parsing and lexing phase. So what Reason does is it provides sort of a forked version of that parser and lexer, which lets us implement a new syntax. So it's not actually a new language. All it's really concerned with is the characters and the way that you write the program. And it's really interesting to note that this happens only at the untyped phase, right? So Reason can't actually mess with the type system. So you still have all the strong guarantees of OCaml's tried and true type system with a more familiar syntax. Now, BuckleScript comes in at this level, at the lambda IR. It'll take that, and instead of outputting bytecode or native code, it uses some really cool compiler terms to output JavaScript instead. And it does so extremely fast, and it does things like dead code elimination at a really refined level. And the code that it outputs, in most cases, even looks handwritten, which is pretty unique, I think, to compile to just compilers. So that's kind of how it all fits together. And like I said, I'm hand-waving a lot. There's a lot of more complexity here. But we can see here that the best part about this is that it preserves the core value of the language OCaml, which is really its type system and its semantics. But we want to talk about Reason because that's how we're going to be using the language OCaml. So I'm going to run through just some basics of what it looks like. If you've used ES6 or ES7 and Flow or TypeScript, a lot of this is going to look very similar. So it's very accessible to a lot of users in our community. So let me just go over the basics by example. So here is an example where I'm just going to define some variables, define a function, and then call a function. So the first thing we see here is that I'm defining a variable using let, just like you would in a lot of JavaScript programs. And what's special about Reason is that block expressions actually have a value. So inside this, I'm actually defining two other bindings, first name and last name. And then the last expression in the block is going to be the value. So user will eventually have the value Bobby Tables. And then here I define a function called greet. And you can see here that it uses the arrow function syntax, which, as I said again, it makes it really familiar to users who've used ES6 or ES7. And in this case, this function actually takes two arguments. And Reason has a concept called named arguments, where you can define optional or non-optional arguments that should be explicitly passed in any order with a name. So in this case, it takes a greeting argument, and then there's just a standard unnamed argument of name. And then it returns a string. We could see here that that caret operator is how you do string concatenation. And then finally, we call that function. We pass greeting the value of hello. We pass it our user. And then that should give us the value hello Bobby Tables. So that's just like a quick taste of the basic syntax. Like I said, it's very familiar if you've used JavaScript, which I'm pretty sure we all have. But I want to talk about what really makes the language attractive and what makes it ideal, I think, for stateful web applications. And the first thing that I think does that is pattern matching, specifically with variants. So I'm going to explain it while going through an example here. So with a variant, it's basically a type that can represent a number of different kinds of data. And it's a way that you can define, for example, different states in your application or different types of data or different types of users, for example. And in this case, we are defining a type called school person, which has three potential values. Now, with variants, the values, we usually refer to them as constructors. If it helps, you can see that they're always capitalized, so you can kind of think of them as JavaScript constructors, except instead of creating instances of like a class or something, it's sort of a type instance. And the first two constructors we have here are teacher and director, and then we have student. And we can see here that student, unlike the previous two, can accept arguments, or accepts an argument. And that's because variant constructors can accept an arbitrary number of arguments so that when you create an instance of this variant, you can hold some sort of data inside it. And again, it's just like constructor functions, which can themselves take arguments and do sort of the same thing. And here's an example of actually using that. So we define a variable called stranger, and it is an instance of the student variant constructor. And we're passing it some data, and this student's name is Kim. We're assuming that that string is a name. Now, we've put some data inside a variant. How do we get it out? That's what pattern matching gives us. So in this example here, we are defining another variable called greeting, whose value is this switch expression. So in Reason, you define a pattern matching expression using the switch statement. And in a lot of cases, pattern matching is a lot like switch statements as you know them in JavaScript. They're just a little bit more powerful here. So we see here that we handle each case and separate them with the pipe operator. And if it's a teacher, we're saying, hey, professor. If it's a director, we're saying, hello, director, a little more formal. And then we're actually matching the student constructor twice. And what's interesting is that in pattern matching, you can not only match on just variants themselves, but on the actual data that they hold. So in this case, we're saying, if we get a student whose name is Richard, we're going to say, hey, Ricky. But otherwise, we just say, hey, whatever their name is. So you can see here that we just kind of define a variable name, and that will take on the value of whatever was stored in that variant. And what's the coolest part about pattern matching is that it's exhaustive. And what that means is if I forget to handle a case, which we all do probably sometimes, the compiler is going to let you know at the time of compiling. So you're going to know immediately if you've messed up. So for example, if I forgot to match the director constructor, the compiler is going to say, hey, this pattern matching isn't exhaustive. And it will actually give me an example of a value that I didn't match. And in this case, it's just a simple one of the actual variants. But this warning that you get from the compiler, in a lot of cases, can be arbitrarily complex. So if you have a variant constructor that's holding 6 different kinds of data, it will be able to tell if you've missed one very specific edge case, and you'll know immediately that you've missed it. And the big advantage here is that it makes it difficult to put your application into an invalid state, right? Because you have to explicitly define all of the different states that this variant can be in. So for a school person, it has to be a teacher, director, or student. If you've missed handling that kind of data in some place, you're going to know immediately, which means that it makes it very difficult to have actually impossible in a lot of cases to have runtime errors related to types like this. Another advantage is that it makes refactoring extremely easy. If I add an additional case to my variant, or if I rename one, the compiler will immediately tell me, hey, you're handling this old case, you haven't handled the new case, and once you fix it and the compiler is no longer complaining, your application is probably going to work. So you get a lot of assurance there. Now, another great thing about Reason and OCaml, and when I say Reason, again, I'm meaning the language OCaml, is that it has a pretty complex and really useful module system. And a lot of people say that OCaml and Reason, there's basically 2 core languages. There's a language that deals with data and functions, and there's a language that deals with modules and module functions, which are called functors in OCaml. And every file in Reason is a module. So by default, if you define a variable in a file, it is defined as an export of that module, and you can access it in any other module. You can define submodules, so there's an explicit syntax that we'll see that lets you define a module inside a module. And you can actually define module interfaces separately. So if you want to define a contract for some sort of module that you want to require from some other part of your program, you can explicitly state, hey, I need a module that only provides these methods or this data. And you can do the same with files. For example, if you don't want to expose all of the inner workings of a module, you can export only maybe an abstract type or only a certain set of the methods that are defined in the module. And like I said, there are these things called functors, which mean a lot of different things in a few different languages, but you can just think of them as functions that take modules and return modules. And they are extremely useful. So here's an example of defining a module with a syntax. And remember, this is going to be in a file, so it's already technically in a module somewhere, but we're defining an explicit submodule as well. So you use the module keyword to define a module, in this case, the school module. And inside it, we define two things. We define a type, which is a variant called profession that can be either a teacher or a director. And we define a function called getProfession that takes one of those professions and returns a string that just describes it. And the way that you access data or methods or types inside from a module is the dot syntax. So just like you would access something in an object in JavaScript, and in this case, we're saying Mr. Fubar is a school teacher. And then we just call print endline, which is like the native way to print something to the console, and we get his profession, so we should get a teacher. And so like I said, modules are a great way to organize your program. You can explicitly say what a module exports and define a contract between modules in your application that make it really easy to make sure that you're not leaking implementation details, right? I can say explicitly that, hey, you can't know what this module does. It only exports this abstract type or this method, which again makes refactoring easy as well. Okay, so those are kind of the two biggest parts of the language, and since I'm short on time, I can't go over everything, but there are other things like how it handles functions. Again, it's a functional language. It has support for imperative programming, which is really useful if you're sort of moving an existing JavaScript application to OCaml or Reason, because you're probably using a lot of imperative stuff. But what I want to talk about now is the tooling for Reason. So tooling isn't only just, Reason isn't only just a syntax for OCaml. It is also kind of a set of tools, in a lot of ways a community around the language that make it a lot easier to use. And the first tool that is really useful, especially if you're learning the language, is Reason Tools. And what it does is it lets you, in your browser, highlight or copy and paste some OCaml code, and it will automatically convert it to the Reason syntax. And the reason this is useful is because Reason's been around for not that long, right? But OCaml's been around for 20 years or so. So a lot of the best learning resources are written in OCaml. And one of the big issues with learning Reason is that you have to learn OCaml, and you kind of have to learn the syntax for Reason as well, which can be kind of difficult. So Reason Tools is meant to sort of bridge that gap and make it easy to use OCaml resources to learn Reason, because again, they are the same language. It's just a different interface. Reformat is one of the best tools. If you've used Prettier, you're going to love Reformat, or Refmat, I think it's Reformat. And this is actually one of the inspirations for Prettier, and it's basically just a code formatting utility. So if you use Reason, again, by default, you really don't have to worry about styling or anything like that, which I think is super useful. And it also comes with this top-level CL, or like a interactive terminal thing, which is really useful when you want to sort of just play around and mess around. It's a lot of like the node REPL, but it's a little bit better. It gives you, as you can see in the GIF, hopefully gives you type recommendations and stuff, or autocomplete. So this is also, again, useful when you are learning the language or you just want to mess with, something really quickly. Now, how do you actually get started with Reason? Like the stack itself sounded pretty complex, so you might think that you have to install OCaml, you have to install a bunch of stuff, and you used to, but now thanks to BuckleScript, it's really just a two-line operation. And the first thing you install is this global package called BS Platform, which is BuckleScript Platform. And then it provides this executable BSB, which you can pass in a init option, give it the name of your application, and then you can tell it what kind of application using this theme. In this case, you can start a basic Reason application by saying basic Reason. And it's interesting to note that BuckleScript has native support for Reason. It understands it out of the box. You don't have to do anything to tell it how to use or compile a Reason, because again, it is an OCaml compiler, but thankfully the communities are working together pretty frequently. Now, the end? No. So, yeah, there we go. No, it's not the end. That was a trick. We we all write JavaScript applications, but we use a subset of it, right? We're probably all writing React applications, which is why you're here and listening to me talk. And this is probably one of the best things about Reason if you're heavily using React, and that's ReasonReact. And ReasonReact is basically a safer, simpler way to build React components. And that's the tagline on their website. It's a way to build React components using Reason. And it has full support for JSX, which means you don't have to add any additional compiler or anything like that. The Reason compiler and pre-processing tools that it provides give it to you out of the box. And it also provides a way to define type-safe interop with existing JavaScript components. So if you have an existing React library, or you want to use existing components that are on NPM, you can define an interface with those components in a way that's still type-safe, which is really important. And it also provides a new, really expressive API for state management. And this is actually super new. So if you've looked at Reason before in the past, this might not be something that you saw. So it's pretty great. Now, of course, the basic component of React is components. You have to know how to build components to use React. So I want to talk about how you actually build components with ReasonReact. And there's 3 steps to doing that, and I'll show some examples of how to do it. The first is that you create a component template. So the API is a little bit different. You don't have to import and extend classes. Reason has a class, or OCaml has a class system, but we don't use it at all. So we define what's called a component template that sort of represents the type of component that you're defining. Then we define a function called make inside of the file. And remember, every file is a module, so it's technically always exported. And this is a function that ReasonReact will call to instantiate your component. And then after you've done that, you just define render and the other lifecycle methods and other required methods depending on the type of component that you've defined. And there are technically 2 types of components that you can define, or component templates that you can use. There's technically 4, but there's 2 as far as we care. And the first is going to be ReasonReact.stateless component. So this is what you call, this is a function that you call to define a stateless component. So unlike JavaScript, you don't just define a function, you have to explicitly say that your component is stateless. Now, if you want to actually use state, which you probably do, you might think that you would use ReasonReact's stateful component, which is what it used to be. But there's a new API, and it is now called reducer component. And we'll see why that is in a second. But let me walk you through just an example of what this looks like, because I know that sounds kind of like gibberish. So this is just 11 lines. This is like the most basic stateless component that we can define. And you can see the top line here. We're defining that component template. We call it component, just as kind of like the standard, by calling that stateless component function with the string greeting. And the string that you pass it is just used for debugging purposes. So this would show up as greeting inside of the React DevTools. And then we define that make function. And again, this is what ReasonReact is going to call to actually create your component. And in this case, you can see that we've defined a labeled or a named argument called name. In ReasonReact, props are just named or labeled arguments on that make function. There's nothing special about it. And in this case, it also takes another argument called children. That's how you render children. And we've put a dash before it, and that tells the compiler that we're not going to use it. We don't care. Now, here we define the render function. And you define a function explicitly with the fun keyword, which is pretty fun. And it takes this record, which is called self. And self is going to be something that you might use more in a stateful component, because it lets you access things like state and binding methods, which we'll see. And then we define a greeting variable, just concatenating that name prop with hello. And then you can see here that we have to actually call this function called string to element on line 8. And that's because in JSX for ReasonReact, you have to explicitly pass in an element. So it has to be of type React element. So you can't just pass in arbitrary strings or numbers. You have to explicitly convert, which is a little bit more verbose than just using regular React, but it's also much more type safe. You know that this is going to be an element. So that was a stateless component. Now, how do we define stateful components? And we do that And we manage state in ReasonReact using reducers. So if you've used Redux, this is probably extremely familiar. It's basically the same idea. If you haven't, it's basically like a state machine. If you don't know what that is, it's just super cool. And to use it, you do three main things, which first you define a variant, which we saw earlier, that describes all the possible actions. And if you think about how reducers and Redux work and how variants work, you can see how this makes a lot of sense because you always want to know every type of action that you can possibly dispatch, right? And you want to make sure that your reducers handle those in all cases. And then you define a method called reduce that handles and actually does that and manages the state updates. And then finally, if you want to define a function that actually initiates a state update, there's this method on that self record called reduce that kind of binds a function that returns an action. And I'll show you what that looks like here. So this is an example of a really basic stateful component using ReasonReact's reducer API that is a counter. So it just lets you increment a counter up by 1, down by 1, etc. And starting at the top, we define a variant called action. And it can be one of two constructors, add or subtract. You don't have to call it action. That's, again, just kind of a standard. And then we state the type. We state the type of state. In this case, it's a record that has one field, which is count, and it has to be of type int, which is a number. Then again, we define that component template. We're going to call it counter. And we define our make function. Now, because this is a stateful component, we have to provide an initial state. There's no constructors here, because again, we're just defining a make function that returns like a record, like an object. So there's no place to like bind methods or create this dot state like in JavaScript. So there's an explicit lifecycle method for it called initial state that just returns the initial state. In this case, we're starting count at 0. And this is really where it gets the most interesting. This is our reducer method. And a reducer is a function that takes an action and the existing state. And then what you do is it has to return what's called an update. So we can see here, that the last expression here is the switch statement, and we are handling all of the potential actions that we've defined at the top. And we're returning this ReasonReact.update function call. And this function call will ensure that the state that you're updating is complete, which means that you haven't missed a field. If you forgot to like spread existing state on it, if there's more than one field, it will tell you. And again, because this is pattern matching, there's no possible way that you can miss an action, right? You have to, by nature of the type system, handle every potential action that your application can dispatch. So you have type safety that makes it, again, almost impossible for invalid state as long as you aren't doing any crazy type magic. And then here we have the render function again. And here we use that self.reduce method, and what that again is, it's kind of like binding it to the instance, but you pass it a function that returns the variant constructor that it should dispatch, right? So that's going to be the action that's dispatched. So we have an increment function, which will dispatch an add event, and we have a decrement function that will dispatch a subtract event. And then we just go ahead and pass those on-click to this button, which is the increment, and on-click to that button, which is the decrement. And that's basically the most simple example of how reducers in ReasonReact work. And this is a very new API, so you might not see a lot of examples or documentation on it other than the official documentation, but I definitely encourage you to give it a try. Now, starting a ReasonReact project is actually even easier than starting a Reason project, thanks to Create React App. Create React App gives you this option where you can pass in a scripts option. And the community has developed this project called Reason Scripts. So all you have to do to actually initiate a ReasonReact project is run this one line, which is basically, and you have to install Create React App, but you should do that anyways. We just run this one line, and it will create an instance of your application, and you get all of the benefits of Create React App that you would initially. It's a PWA, has Webpack set up for you, all of that, and it will also compile all of your Reason code, which is really neat. So I definitely recommend giving it a try. The barrier to entry is really low, thanks to tools like Create React App and BuckleScript. And that's it. And a fun note, these slides were all written in Reason. So this is an actual Reason application, and you can inspect the source at my GitHub there. And that's it. All right. Thank you.